Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Have you got an interesting science story that's going on in the world beyond us that we know nothing about?
It's an interesting story about some Australians. Andre Rode, a researcher in the Australian National University, has been building a tractor beam.
Wow.
It's a bit like the ones you get on Star Trek, but not quite on the same scale.
Oh, a tractor beam, you see.
So
there was me thinking rurally, it's a beam for your tractor so that you can...
Strengthening, no, moving things around with the power of light.
Wow.
People have been doing this for a while, but only on really, really minute things, sort of the size of atoms or the biggest about a bacteria.
Yeah. When
they were working by kind of the light would come on, the light would get deflected, and when you deflect light, you get an equal and opposite reaction, and it would move around very gently. That can only move tiny things. Andre's got it still in the tiny region, but up to about 100 times bigger. So what he's doing is, instead of actually using the deflection of the light, he's making a tube of light, so a very, very intense laser beam in a tube.
Yeah.
And you get the particle he wants to pick up in the middle of that tube. So if you think about it, you've got this particle, which is in a relatively cold, dark region in the middle, surrounded by a very, very hot region around the outside. So if this particle moves onto the edge of this light beam, inside edge of this tube, on one side you've got very, very, very hot air heated by this laser. On the other side you've got cold air. Air is made of lots of particles, and you may have heard of Brownian motion when you were at school. These particles are moving around.
Right, yeah.
And they bash into things. And the hotter they are, the harder they bash into things.
Oh, wow.
So on the hot side, they're going to bash into your lump using little glass beads harder than on the cold side. So whenever it starts to move out of this tube, it gets moved back into the middle. So you can move around the little particles using just the power of light.
That's fantastic.
Doesn't work in space, though, unfortunately. So
well,
Captain Kirk's not got anything to worry about.
Not yet. Dave, there's a text here which I want to start with here, and it's from Jeff of Grays, who says, Sue, what countries use the word aluminium, and who pronounces it aluminium, and why? I hate the word aluminium. I can't believe I've managed to say it 3 times. It doesn't sound right to me. That's from Jeff of Grays.
It is an interesting one. Certainly in Britain we use aluminium. In the States they use aluminum. I think the history is that the very, very earliest usage was aluminum. But then that doesn't really make sense because there's lots of other metals which end up in ium, so gadolinium and lots and lots of other ones. In Britain they changed it to aluminium, and the official international chemical way of pronouncing it is aluminium, a bit like the official international way of spelling sulphur is with an F, which certainly annoys Chris. I can't spell, so I don't mind so much.
Oh, fair enough, yeah.
And so, the Americans haven't taken it up, and so I'm still using aluminum. It's aluminium for consistency, really.
All right, then, OK. Lost in translation just a little bit. Let's go to email now. This one's coming from Hector, who I believe is from South Africa, who says, and I've often wondered this, actually, why do we get sound before TV images?
It's an effect with the old-fashioned big TVs, the cathode ray tubes. It's to do with how they work. Basically, the sound system is just a very simple circuit. It can turn on almost immediately. But the way the picture is being produced is at the back you've got an electron gun, which has a very, very hot filament. And that gets very hot. It emits electrons. They're accelerated down the tube and turned into a beam, which is then scanned across the front of your TV very quickly. And when it hits the front of your TV, it creates light. It hits something called a phosphor, which glows when it hits by electrons. So it glows, and you get a dot moving across your TV very quickly. And that builds up a picture. But it takes a while for the coil at the back to heat up. So it takes a few seconds to get hot enough to emit enough electrons. And so it takes a few seconds for the picture to build up. With older TVs, it took even longer because all of the control was done with valves, and those intrinsically involve these hot wires which emit electrons. So basically, a TV is a great big valve, and valves take a while to turn on. But the sound is all done in transistors, which turn on immediately.
Right, let's go to our next question because we're going to the phones. And now we have Dave on the phone. Hello, Dave.
Hello.
Hello there, in Luton, yes?
That's right.
OK, what's your question for Dave?
The DNA helix, can it have a clockwise or an anti-clockwise rotation?
All the DNA in the world that we know of has a clockwise rotation, so it's a bit like a right-handed thread, like a normal screw thread. There's no fundamental reason why, as far as I know, why it wouldn't work left-handed, except the fact that most proteins are right-handed and most biological molecules are right-handed. So even quite simple molecules like sugars can have a little bit of a twist in them. They actually rotate light very slightly. And therefore it wouldn't be compatible with all the proteins and the amino acids which are floating around it, so it wouldn't work on Earth. But if you built a mirror image of the Earth, there's no reason why you couldn't have a left-handed DNA.
Didn't DNA actually produce the first proteins anyway? So if there was a left-handed spiral, it would produce its own proteins?
It's one of the big questions as to why almost all biological molecules have a right-handed twist. I think actually you can create proteins without life. You can certainly create the building blocks of proteins called amino acids without life, and they've found them on things like comets and in meteorites. You can sometimes find some amino acids. I think they might have found evidence for them in big clouds of gas out in space. And there's a thought that possibly there might have been some rotating the light. You have rotationally polarised light, so you have clockwise polarised light given off by stars or big supernovae or something. And that could have created more of one-handed amino acid than the other-handed. Then as soon as life starts, there's thought to be a system whereby if there's slightly more right-handed ones, the creatures which are right-handed will do better than the creatures which are left-handed, so they'll be the more right-handed, which means they do even better and better and better, until you end up with only one-handedness of
So light can actually spiral?
Yes.
Both ways?
Yes. It's a bit like polarisation.
Yeah.
It's a kind of combination of two polarisations in two slightly different ways. You can get right-handed to left-handed spirals. In fact, the 3D movies use that.
Do they? You see, me who doesn't mind sounding stupid at all, but I've just thought, is it not because the Earth, that rotates clockwise, doesn't it?
Depends which way you look from.
Right-handed.
Unless you're in Australia when it looks the other way around. It's a thread.
Interesting question. Thank you very much.
Yeah.
All right, let's go to our callers in now. This has come in from Valerie, and she says that in the gallery she would like to know what is the thing in alcohol that makes a person feel relaxed and gives them a sense of well-being. Probably too much, I suppose.
It's the alcohol, the ethanol, which is what you're talking about. It's not my area of expertise, but as far as I understand it, ethanol can get into your brain, which is quite unusual. A lot of molecules can't. Your brain is made of lots of little cells, and then they communicate with one another with various different things. Alcohol gets in the way of some of the communication systems because they communicate with some molecules, and alcohol can kind of get in the way and sit in the way, so it can alter the way they communicate with one another. It can sit in. It tends to sometimes it gets in the way of some of the receptors which inhibit activity. So basically, it just gets into your brain and plays around with the way your nerve cells are talking with one another in such a way as that some people feel happy with it.
All right, well, let's go to this one here, which has come on the email from Lawrence, who's in Edinburgh. Hi, Lawrence. He asks, if you drilled through the Earth, would you need to turn round halfway? Dave?
Depends what you mean by turn around. I mean, absolutely, you would keep on going in a straight line. You'd go down and the gravity would get less and less and less until when you're at the centre of the Earth, you would essentially be in zero gravity. Because although there's a huge amount of mass pulling on you, there's exactly the same amount above you as below you, so it should cancel out exactly, and so it'll feel like there's no gravity at all. And then as you start going up the other way, it'll start feeling like you're going uphill. Even though you haven't changed direction, you'll go straight downhill and uphill until you get out the other side.
Excellent. One here that's from... where's it gone now? Did it? Jill. She says she's just seen a Chinese lantern go over it. She says she doesn't know how high they go, but could they potentially be ballistic aircraft?
I would doubt it. I think they're probably not going to get much higher. I don't have any definite evidence. I can't see why you shouldn't be able to design a Chinese lantern so it could get high enough to interfere with aircraft when they're flying up high. But unless you're very close to an airport, I think the standard ones aren't going to get very high. There's just not enough heat there to keep them going long enough to get high enough. Let's
go to the phones again now, Dave, because we've got Pat in Lowestoft on the line. Hello, Pat.
Hello, Sue.
Hiya, mate. How are you doing?
All right, thank you. My question to Dr. Davies tonight is the Earth has been proved by most people that it's round.
Yep.
So we're walking on our feet, so why ain't the Australians walking on their heads?
It's all to do with gravity, basically.
Yeah.
Isaac Newton worked out 300-400 years ago was that anything with mass, anything which is heavy, attracts anything else which is heavy. Basically, we're all pulled towards the heaviest thing near to us, and the heaviest thing near to us is the Earth, because that's really, really big and heavy. So basically, everyone is pulled from all directions towards the Earth. So if you're on the top of the Earth, you're pulled down towards the Earth, and if you're below it, you're pulled up from the way we're thinking, you're pulled upwards towards it. So basically, just Australians think down is what we think is up.
Yeah.
Just because they're pulled towards the Earth.
Right, thank you.
All right, thank you. You've got to think of it in the big picture, from a long way away.
Yeah.
You're walking one way and then they're there, so they would appear upside down to us and we would appear upside down to them.
Indeed.
Yeah. All right, Pat, take care.
Thank you.
Bye-bye.
You.
Okay, bye. Dave in Norfolk has sent an email in to say, I see many obelisk-shaped pylons all over the countryside, but Tesla apparently managed to send 100 million volts wirelessly over 26 miles in 1899. Has there been more research into this theory? Dave?
I think there's no reason why you can't transmit power wirelessly. In fact, we're doing it at the moment. We're transmitting power from the radio mast to your radio.
Yep.
At the moment, it's just a very, very, very small amount of power. So the question is whether that is a useful thing to do to get power into your house. And the problem is that definitely over long distances, you can send out power using microwaves or some form of light. And in general, if the further away you are, the more of that's going to kind of leak out the edges and going to miss your house. So the more of that energy is going to get wasted. So the less of it that you can use, so that's basically wasted coal in the power station or whatever. There are some technologies coming up whereby you can charge your mobile phone just by putting it on a pad, so you don't have to have lots of wires and things to get tangled. So basically you have a coil of wire in a pad and then a coil of wire in the mobile phone, and they basically act like a transformer. So you have a changing magnetic field produced by the coil that induces a current in the mobile phone, and you can charge your mobile phone without it actually plugging into anything, which would be kind of convenient. There are some others whereby you can do that with the whole room, I think.
Really? What about all the power waves and all that stuff when you're wandering around in it? How's it going to affect you?
It does slightly worry me that you might get some issues with absorbing some power in your body or in metal items. Yeah. Companies involving it reckon they can get around this. I'm not entirely confused. I'm not convinced. I think it will probably waste quite a lot of energy. I think fundamentally there's no reason why you can't do it. It's just it wastes energy, and it's cheaper to do it with bits of copper.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, we've got Dr. Dave, who's been doing all his calculations. His little brain has been ticking. I can hear the togs going round. Francis's question was, what's the land area of the Earth? Dave.
Okay, we can work this out using a little bit of maths and a little bit of knowledge. The Earth has a radius of about 6,400 kilometres. Mm-hmm. And the surface area of a sphere is about 4 times pi times the radius squared. So for the Earth, that's about 500 million square kilometres. And the land takes up about 30% of that surface. The Earth is more than 2/3 water. And so if you multiply 500 million by 30%, you get to 150 million square kilometres. So quite a lot of area. Although, of course, the area which we can actually live on and is useful is quite a lot less than that, because a large proportion of that is mountains or tundra or something which isn't very useful.
Okay, but if you ironed it all out and flattened it, what would it be then? No, I don't ask you. Now, we've got a question here from Philip, who is in Welling, who says, why does hair look darker when it's wet? After all, water is transparent. Very true.
This is a very good question. It's very, very related to... I don't know if you've ever noticed if you've got a glass which is a bit scuffed up.
Yeah.
And it kind of looks all white and horrible. If you put it in water and you get it wet, it suddenly looks clean and unscuffed again. It looks much more transparent when it's wet than when it's dry. And the reason for that is to do with the reason why it starts to look white if you take glass and sort of sandpaper it.
Yeah.
And that's because glass it's perfectly transparent, but when light hits it, it reflects, and also it refracts, it bends. And so if light hits a rough surface, it kind of reflects and refracts in all sorts of random directions. So lots of it bounces back in random directions, and when you see all the colours of the rainbow bouncing back off something in random direction, it's white. And what the water does is water has a similar refractive index to glass. So when the light goes from the water to the glass, it doesn't bend as much, it doesn't reflect as much. So much more of it goes straight through. So the glass looks a lot newer and a lot cleaner.
Yeah.
The similar thing happens with hair. The refractive index of water is similar to that of your hair. So the water's got a smooth surface, so the light goes straight in.
Yeah.
Not very much of it bounces off. When the light goes from the air into the hair, instead of normally when it goes from the air into the hair, lots of it bounces off. If it goes from the water to the hair, they've got similar refractive indexes. Not very much of it reflects, it goes straight in and it gets absorbed. So when your hair's dry, lots of light hits it and bounces off, so your hair looks light. When it's covered in water, the light tends to go straight in and get absorbed by the hair, so it looks darker.
Now then, John has texted in, and he says, why does the sound of the upstairs TV arrive at a different time from the downstairs one? Must be his telly.
Probably is his telly. My guess would be that one of them is digital. And digital TVs, digital radios take a while to decode the information, and everything is happening a few seconds behind. And so my guess is that one of your TVs is digital and one isn't, and the digital one is a few seconds behind the conventional one.
All right, fair enough, thank you. Now then, this one comes from Wilf James, who's in Letchworth Garden City. Hi to you. And he asks, are sunspots actually solar hotspots?
That's a very interesting question. In some senses they are, in others they aren't. I think I've read this email a while ago, and he goes on to ask basically how can the sun emit light, because light is normally emitted by electrons in atoms changing energy levels, and as soon as the electrons leave the atoms, how can they change energy levels, how can they lose light? And the simple answer is that if an electron is flying around free, then they can change from any energy to any other. All they have to do is bounce into something and they can change their energy. And when they change their speed, they can change their energy, and some of that they can accelerate. And when you accelerate a charge, you can emit light. So free electrons are very good at emitting light, actually. Most of the light which is emitted from a hot piece of metal is coming from effectively free electrons. Sunspots, if you look at the sun, in fact, you won't have seen them for a while because there have been very, very few for about the last 5 or 6 years.
Yeah.
Been a peculiarly long minimum in sunspots. But all of a sudden, recently, that's coming back. Don't look at the sun, but if you can project an image of the sun, you see little dark patches on it. At the temperatures which are emitting visible light, then the sun is cold in those regions, so it's not emitting as much light. But if you look at those regions in very, very high energies, so in the X-rays, in fact, the layer above the bit of the sun we can see in the atmosphere is incredibly hot and emitting a huge amount of X-rays. So it's quite complicated. It's a simple answer.
Isn't it just? Phew. Thanks, Will, for that question. Now then, Mark in Dunstable has asked, he wonders about living in space for long periods of time. What effect does it have on the human body? What research has been done? Dave?
There's been about sort of 20 or 30 years of research, first on the Russian sort of Mir space stations and then more recently on the International Space Station. The biggest first effect you get is because there's no gravity and your bones tend to get weaker and weaker. This is because the way your body works out how strong a bone it needs is that if it's being used, then your body keeps making it strong. But as soon as you stop using a bone, it slowly sort of degrades because your body thinks, I'm not using it, there's no point in keeping a really strong, expensive, metabolically expensive bone.
Just got to keep my knee working then, Dave, yeah, okay. Right.
So if you go into space, you're not walking around, you're not fighting gravity all the time, so your body thinks, you don't need these great big heavy bones, I'll slowly erode them away. Or it doesn't have to keep looking after them, so your bones get very, very weak. Similarly, your muscles get very, very weak because you're not doing very much exercise. And so astronauts on the space station have to do lots of exercise on kind of springs, they sort of go running on sort of running machines, but with great big pieces of elastic to hold them down to pretend to be gravity.
There's going to be reality TV about on the space station, isn't it? That's the next thing.
Very probably. I think there's a guy called Mr. Bigelow who wants to do very similar things.
Yeah,
he wants to set up inflatable space stations and then astronauts can basically tourists can go up.
Scary.
But yeah, and then if you're in Earth orbit, there's not a huge problem with radiation. There is more radiation up there than there is on Earth because you haven't got the atmosphere in the way, but you're protected from most of the radiation by the Earth's magnetic field. But as soon as you get out of the Earth's magnetic field, then there's really big problems with radiation. In fact, the Apollo astronauts were quite lucky that they weren't hit by a solar storm, because they would have just, if they got hit by a bad solar storm while they were going off to the moon. And there were several of them in between the Apollo launches, then they would have just died from radiation sickness sometimes before they'd even got back to Earth.
Oh, heck. Let's go to our next one then. This is from Dominic in Newmarket, and he asks, how does a mobile phone mast work? There are more of them now than ever, I think. But how does it work?
That's a very, very big question. They essentially, the way they work is by the mobile phone converts your speech into a series of digital data. So it digitise it, so turn it into a whole string of numbers. That's then sent over a very cunning radio system. So they use lots and lots of different radio channels at the same time, and send bits of your speech on different ones of the radio channels, which means that you can get more phones talking in the same amount of radio bandwidth, the same number of radio channels than you would do otherwise. This then gets sent to the mobile phone mast. If you're in a busy place with lots and lots of people using mobile phones, the mobile phone mast won't be one aerial. It will be many, up to 10, 16, if not more. Each of these aerials is so the mast can pick out signals from different directions and has less problems with your phone talking over the top of your neighbour's phone, or certainly from someone on the other side of the mast. It all then gets sent down optical fibres to other masts.
Excellent. All right, well, we've got another one here which has come in on the text, and this is from Sue, and says, shadows are not a precise copy. In fact, sometimes the edges of shadows are that close together, stretch out and join each other. Why is this? My kids used to play with their shadows, making their heads join, which is great fun. Dave?
I think there's a couple of effects. I guess the first thing is that a shadow is a projection of you, so it's which bits of you get in the way of the sun. So it'll be whatever shape you are getting in the way of the sun. So it's not an exact picture of you, it's just kind of a picture of the edge of you as the sun sees you.
Yeah.
And then if the ground isn't at right angles to the sun, then it can get stretched out. If the sun's very low, then your shadow gets very, very long. I imagine the strange effect her children were seeing of their heads joining together was that the shadow suddenly seems to jump a little bit between the two heads. And this is because the sun isn't a single point. The shadow it produces isn't beautifully sharp and beautifully well defined. The edge of it is a bit fuzzy. Because there's a region whereby if your eye was in that region, you'd be able to see not all of the sun but part of the sun. So the shadow, right at the edge of the shadow, it's very, very weak, and then as it gets closer in, it gets darker and darker. You can see the same thing in here with the lights. If you hold your hand over a piece of paper, if it's a long way away, then the shadow isn't very strong. But as you get deeper, you suddenly get a really dark shadow in the middle. Because in the middle, it's shadowing all the lights, but higher up, it's only shadowing.
Mine's darker
only
than
partially
yours,
shadowing them. And so I think what possibly was happening was that the two areas of partial shadow, where they overlapped, because one of your children's heads blocked one half of the sun and the other head blocked the other half of the sun, suddenly turned into full shadow, and so it looked like the shadow was growing.
All right, well, one more I think we've possibly got time for. This one has come in from Roger, and he says, I don't understand maths related to CO2 emissions given in grams per kilometre. So how are CO2 emissions calculated per kilometre? I wonder. I don't think about that, you see, but yeah, it's a valid question if you're bothered. How is it, Dave?
Okay, basically, first of all, they work out how much fuel your car uses for every kilometre. And they work out how much carbon is in that fuel. So you get a mass of carbon. So he's using an example of maybe it's using 4,200 grams of carbon for every 100 kilometres or something.
Yeah.
But that isn't how heavy the carbon dioxide is. because in every molecule of carbon dioxide you have one atom of carbon and 2 atoms of oxygen, and the 2 atoms of oxygen weren't in your fuel. They've come in from the air. So the carbon dioxide is heavier than the carbon you've burnt. In fact, it's quite a lot heavier because the mass of a carbon atom, the relative mass, is 12, whereas the mass of an oxygen atom is on average about 16, is roughly about 16. And so you get about 3.6 times as much carbon dioxide by mass as the carbon you burnt. So the mass of carbon dioxide per kilometre is going to be about 3.5 times more than the mass of the carbon.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.